In the last couple of videos, I've argued that models are tools for reasoning about the world and our experience of the world. And the way they work is by picking out similarities between the model and some target system in the world. We make inferences with the model and then claim that some corresponding inference holds for the target system based on these similarities. Now, you can swap out the word theory for model, and the same applies. Theories are tools for helping us reason about the world and our experience of the world. I will say something in a later video about when people tend to use the word theory versus model in this context. In the next couple of videos, I want to look at some examples that highlight how we can interpret models and theories as hypotheses about what we can ignore in our reasoning about the target system. I think this is a valuable insight into how science actually works. In this video, we'll look at how this works with a simple mathematical model. Here's one of the equations you'll learn in an intro physics course. It describes how far an object will travel when it's dropped near the surface of the Earth in a 1g gravitational field as a function of time. Distance equals 1/2 gt squared. G is a constant. It's the acceleration due to gravity, which is about 9.8 meters per second squared, which we can round up to 10 for rough calculation purposes. So after 1 second, this model says that an object will have fallen about 5 meters. After 2 seconds, it's about 20 meters. This equation describes an object that is accelerating at a constant rate, so it's moving faster and faster over time. After 100 seconds, under 2 minutes, falling at this rate, an object would be moving at 500 meters per second, and it will have traveled almost 50,000 meters, or 50 kilometers. Now, on the left is a photo sequence of a real falling ball. In the middle is a falling feather, and on the right is a falling skydiver. This equation is supposed to help us understand what we're observing in all of these cases. And note how different this modeling relation is from the one we saw with the toy structural model of the Eiffel Tower. With the tower, the analogy between the model and the target is easy to visualize. There's a direct mapping between points on the model and points on the tower. So it's easy to compare the model and the target to judge whether the model is good or not. With equations, it's not so easy to visualize the analogy because equations describe functional relationships between variables, which are abstract relationships. And these variables are changing over time, so it's also a dynamical relationship. But one of the great virtues of mathematical models is that they let us represent these functional relationships in a variety of ways, as ordered pairs of numbers, as graphs, etc., by formally deriving values for the relationship. So it's easy enough to derive data from a model that represents the model's predictions. But what we need to do is compare these predictions with the actual motions we see, like the motion of this falling ball on the left. And that can be tricky. But an awful lot of science is about precisely this, about creating empirical data through sometimes very clever measurement operations and putting this data in a form so that it can be compared with the data generated by theories and models. In the image of the falling ball on the left, they use a strobe flash, for example, to capture the image at fixed time intervals, and other methods to measure the distances accurately. But once that's done, now we're in a position to do a real comparison to assess the quality of the analogy. Just to be clear, what I'm saying is that this stage here is similar to this stage here, where we're comparing the real Eiffel Tower with the toy model of the Eiffel Tower. This is the more common scenario in science. Before you can test a theory or a model, there's often quite a bit of work to be done from both ends, so that data from the theory or the model can be compared with data that is extracted from the real physical systems that we're investigating. But now I want to return to this claim that I made in the last video, that models are tools for reasoning by analogy and by abstraction. And the abstractions they make are essentially claims about what details matter and what details we can ignore in our reasoning. The equation is a model by abstraction. It defines the conditions under which our reasoning with this model will be valid. There's nothing in the model that mentions the shape of an object, for example. There's no specific mention of the mass of an object, so the model is indifferent to differences in mass. There's nothing in the model that represents the medium through which an object is moving, so there's no mention of the effects of drag or wind resistance on the motion of an object. What does this mean? The abstraction hypothesis, which captures the way we use models like this in our reasoning about the world, says that the model predictions will apply when differences in an object's shape and mass and the medium through which it's traveling don't matter, when we can ignore these differences. But the case of the falling feather and the falling skydiver are precisely cases where these features obviously do matter, where the shape of an object and the effects of drag and air resistance are a factor. The feather's movement will be dominated by the local movement of the air, and the skydiver will accelerate until wind resistance balances the acceleration due to gravity and her velocity levels out, and she reaches terminal velocity, which will depend in part on the shape she makes with her body. So we don't expect the predictions of the model to apply to these cases. But if we can remove these differences by, for example, removing the air and having these objects fall in a vacuum, then the model's predictions should apply. And it turns out they do. A feather and a heavy object will fall at the same rate in a vacuum. It's a common demo in a physics class, but it's still quite striking to see it in action because all of our experience with falling feathers has them floating gently to the ground. To predict the actual behavior of feathers in skydivers falling through the air, we obviously need a more sophisticated model. So it can be tempting to ask whether models are true or false, but I hope it's becoming clear that this is not the right question to ask if we want to understand how models are actually used in science. The right question to ask is, does the model allow us to reason well within its intended domain of application? Now, reasoning well can mean a lot of things, but included in that is, does it allow us to make reliable inferences about what we will observe or measure? And the answer to that is always going to be relative to some intended domain of application. Now, in the next video, we'll look at an example that blurs the line between a model and a theory.